Hello everyone, and today I would like to discuss and share some findings of my research paper with you, and let's start our discussion. So, the title of my research paper is 2.2 megaelectron volt gamma ray emission from accreting strongly magnetized neutron stars, and I'd like to say a few words on the background of this topic, and then I will get to the discussion of my paper. So, first of all, this gamma ray line is emitted from a surface of the neutron star. And the emission of this line was known for a long time, but we still have not detected it due to multiple hardships related to its detection. And one of the most significant of these hardships is that to observe this line, the detectors must be highly sensitive because the flux of this gamma ray line varies from 10 to -6 to 10 to -4 photons per square centimeter per second. Also, there are other factors that influence overall emission of this line and make its detection hard, like absorption of the line and pair creation within the magnetosphere of the neutron star that results in reduction and loss of photons and overall reduction in emission of this line. And this gamma ray line gained significant attention with new generations of gamma ray observatories, which advanced our understanding of high energy events happening within neutron stars. Now let's talk about the mechanism of production of this line. So we consider a binary system composed of a neutron star and another companion star, and there is accretion process happening onto the neutron star surface. And as the matter travels along the magnetic field lines, it accelerates and gains significant amount of energy. And this amount of energy exceeds binding energy of nuclei, and in particular helium-4 nuclei. And as a fast-moving material enters the atmosphere of the neutron star, helium nuclei, they strike protons, which result in the following reaction, where helium-4 breaks down, producing helium-3, proton, and neutron. Helium-3 and proton are outside of our interest here. Here, they just travel some additional depths before participating in nuclear reactions. However, we are more interested in the liberated neutron, which thermalizes through repeating Coulomb's collisions with atmospheric protons and neutrons. And once neutron thermalizes, it recombines with atmospheric proton, producing deuterium, and during this process, emitting 2.2 megaelectron volt gamma ray photon. And notice that sharply defined line consists only out of unscattered photons. That means that those photons that didn't collide with other charged particles and didn't lose their energies. And only a small fraction of these photons are actually able to escape unscattered, less than 10% of them. And there are multiple factors that are related to the probability of unscattered photons. And first of them is Compton optical depth, which is a measure of Compton scattering, and it basically describes how protons scatter of other charged particles and changing their trajectories and energies. Also, nuclear reactions play a crucial role in regulating number of protons in the atmosphere of neutron star. For instance, intense proton-proton chain might reduce number of protons available in the atmosphere, which would lead to reduction of number of recombinations with the neutrons. Other factors include number of liberated neutrons during the initial spallation of helium-4 and depth at which those neutrons recombine. And finally, the helium-3, which was actually produced in the initial spallation of helium-4, might absorb a neutron at certain depths, which would result in loss of this neutron. And this implies that only those neutrons that are liberated in excess of initial spallation will eventually recombine with atmospheric proton, producing deuterium and emitting photon. According to the previous research in the field, the flux of this gamma ray line should be scaled with a mass accretion rate onto the neutron star surface. And this means that the more mass is accreted onto the neutron star surface, the larger the emission in this gamma ray line we expect to get. However, estimations in my paper suggest that it's not the case in very bright pulsars because large amounts of accreted mass result in X-ray emission, and this emission produces radiation pressure which opposes motion of material, decelerating it above the neutron star surface and reducing or preventing formation of this gamma ray line. And the aim of this paper is to investigate this X-ray and 2.2 megaelectron volt luminosities relation and look at how X-ray luminosity impacts overall emission of this gamma ray line. Also, we estimate the optimal X-ray luminosity for observation of the greatest gamma ray line. And in the end, these results should influence future strategies of observations of these lines, because we would understand why certain X-ray pulsars are more beneficial for observations of these lines rather than others. And a few more words before we start discussing what I've done in my paper about binary system details. We consider, as I mentioned, a binary system composed of a neutron star with mass 1.5 solar masses, radius 10 to 6 centimeters, magnetic field strength 10 to 12 Gauss, critical luminosity 10 to 37 ergs per second, and critical luminosity here corresponds to the value of the X-ray luminosity at which the radiation pressure created and exerted on the material is so great that it opposes essentially any motion of accretion flow, stopping completely it above the neutron star's poles and creating accretion columns. And note that this value depends on the exact magnetic field strength and tends to increase with larger magnetic field values. And what is nice about estimations in my paper is that they are applicable in these cases of different critical luminosities, and it means that we can apply them to larger numbers of pulsars. And now let's discuss what I've done in my papers. So first of all, we need to understand what is the relation between X-ray luminosity and final velocity of the accreting material, and understand how radiation pressure decelerates matter above the neutron star surface. To do that, we consider following two equations in blue, where first describes the final velocity in terms of luminosity and radiation pressure relation to the X-ray luminosity. And the corresponding plot on the right, which is the plot that describes final velocity to the luminosity. And in general, we can see that for the X-ray luminosity much smaller than the critical luminosity, we expect that the final velocity of material will be the same as the initial velocity without much change, because the radiation pressure exerted on the material is not so great to oppose significantly the motion. However, the closer we get to the critical luminosity, the more intense radiation pressure becomes, and the more efficiently it decelerates matter above the neutron star surface. And at the critical luminosity itself, the material is stopped above the neutron star surface and reaches zero velocity. And also we can note that for greater initial velocity, we expect to have a larger final velocity. Furthermore, since sharply defined line consists only out of unscattered photons, we need to understand their dependence on energy. And to do that, we look at Q, or Q factor, which represents yield of unscattered 2.2 megaelectron-volt photons per accreted helium-4 nucleus. There was taken set of data from Bilston article, and you can see the expression down below, which was used to approximate the given set of data. And corresponding plot on the right, where blue dots is a given set of data. And in general, we can see that for greater energies, we expect to have a larger amount of unscattered photons. And it's reasonable because as the material accelerates along the magnetic field lines, it gains more and more energy. And this increase in energy increases the probability for helium-4 nucleus to be broken down and liberate larger amount of neutrons, which will result in increase of probability of producing unscattered photons. And now we can combine two previous results into just one equation, which you can see above, where we replace general energy with a relativistic expression for kinetic energy of helium nucleus. And the corresponding plot you can see on the right. And note is that we can see that the curves are similar to the ones of the relation between final velocity and X-ray luminosity. And this is due to the fact that Q factor depends on energy, and energy depends on the velocity profile of material, which is decreased by radiation pressure. And it implies that Q factor is negatively correlated with the X-ray luminosity. And again, we in general can see that for the X-ray luminosity is much smaller than the critical luminosity. We expect that the Q factor stays constant and doesn't change much, and still it's very low. And the closer we get to the critical luminosity, the more rapidly it starts decreasing. And at the critical luminosity itself, we see that it reaches zero, meaning that there is no production of unscattered photons, and we do not expect to observe this gamma ray line. Also, we can note that for greater initial velocity, we see increase in yield of unscattered photons. Again, it's due to the fact that more neutrons were liberated in initial spallation of helium-4 nucleus. But in the end, we're more interested in the overall emission from the neutron star surface and not just per accreted helium nucleus. And here where we get the relation between 2.2 megaelectron volt luminosity and X-ray luminosity. And you can see the expression which was used to determine this relation, which combines all the previous equations into just one. And from the plot, we can see that in general, it is a case that 2.2 megaelectron volt luminosity is proportional to the X-ray luminosity times a constant, which is 1.2 times 10 to negative 6, up to a certain point, which is approximately 2 times 10 to 36 ergs per second, after which it still increases, but not at the same rate, which is certain maximum, and then rapidly decreases to 0 at critical luminosity itself. And we estimate that the greatest or the maximum of 2.2 megaelectron volt luminosity is approximately 4 times 10 to 29 ergs per second, and occurs for the X-ray luminosity approximately 6 times 10 to 36 ergs per second, assuming free fall velocity 50% of the speed of light. And for the general case, meaning where we consider different magnetic field strengths and thus the critical luminosity, we expect to observe the greatest gamma ray line luminosity at X-ray luminosity approximately equal to the half of the given critical luminosity. And also, we do not expect formation of the gamma ray line for the X-ray luminosities larger than the given critical luminosity, because all the material is already stopped above the neutron star surface and lost all its energy. Now let's talk about significance of detecting this line. First of them, and maybe one of the most significant, is that detecting this line would significantly constrain equation of state, which is a special relation between mass density and pressure with the neutron star. And having got exact equation of state for neutron stars would allow us to do more precise calculations and numerical simulations involving neutron stars. Also, we would be able to test fundamental physics, including aspects of nuclear physics. We would get more information into how nuclear reactions occur under a strong magnetic field influence. And also, we would get deeper understanding of dynamics of the accretion process in neutron stars. To conclude everything that was said above, it's not necessary to search for the brightest X-ray pulsars to detect this gamma ray line, because as we saw earlier, large mass accretion rates result in X-ray emission, which produces radiation pressure, and it opposes motion of material, decelerating it above the neutron star surface and reducing or preventing formation of the line at all. Also, magnetic field strength influences the critical luminosities, and for different X-ray pulsars, which have different magnetic field strengths, we expect to have different critical luminosities. But these estimations, they are applicable for all these cases. And in general, we expect the greatest gamma ray emission at X-ray luminosity approximately equal to half of the given critical luminosity. And these results should influence future strategies of observations. And this gamma ray line should be detected in the coming years with new generations of gamma ray observatories, which would be sensitive enough to detect this line and would give us very valuable information about the neutron stars themselves and processes happening within them. Acknowledgement, thank you to Dr. Alexander Mushtukov for guidance and support throughout the writing process of this paper. And also thank you very much to everyone for your attention.
Bravo, and thank you very much, Ostap, for your very informative and thorough presentation, which seems to point to some much more effective ways at making observations in the future. So again, thank you for that.
Thank you so much for having me.